Now let's look at an example for normal strain calculation. Okay, in this example 1, we have a bar shown in this figure consists of two parts. The parts AB has a length of 720 millimeter, and the cross section is given. So the part BC has a length of 450 millimeter, and the cross section is also given. So this bar is subjected to a couple of forces of P equals 75 kilonewton on its end. That causes a total elongation. Okay, here is the elongation. It's a deformation. Okay, of delta AC equals 1.692 millimeter. So between joints A and C. So if the normal strain in segment AB is measured as 1,870 microstrain, determine the normal strain in segment BC of the bar. Okay, so what we are determining is the normal strain of BC. Right, so this is what we are determining. So let's look at this example. Starting from chapter 2, we will be able to correlate stress and strain, then force and deformation, using the material property called modulus of elasticity, or Young's modulus. But before that, in chapter 1, so we don't know how to correlate stress and strain. And we don't know how to correlate force and deformation quantitatively. Right, so here actually in this example, we provided a lot of useless information as confusion. Right, so here you can see that we provided the cross-section areas of AB and BC, as shown here. Area of AB and area of BC. Right, we also provided a force, P. Right, so when do we need these values, this data? Just if we need to calculate the stress, right, in this bar, we will use this loading and the cross-section areas. But here in this example, we're not calculating stress, we're only calculating strain. So this data will be useless. Okay, we only need the length and length change and strain. Okay, we only need this data. So after this analysis, let's try to solve this problem. Okay, so in this example, we're calculating epsilon BC. Right. So how can we calculate epsilon BC? According to our definition of normal strain, this thing equals epsilon BC can be calculated from delta BC, right, the elongation of BC, over the original length of BC, right, LBC. Wait, do we know LBC? LBC has been provided here. So do we know delta BC? No, we don't know delta BC, right? So we need to calculate delta BC. So how can we calculate delta BC? Delta BC is the elongation or length change of section BC. So we have known the overall length change, that is delta AC. Right here, this delta AC has been given, that is 1.692 millimeter. So if we know the length change of the other section, AB, then we can calculate delta BC by calculating delta AC minus delta AB, right? So we can calculate delta BC from delta BC equals delta AC minus delta AB. Then do we know delta AB? No, we don't know delta AB, right? But we know the strain of AB, right here. The strain in segment AB is measured 1870 microstring. Right? So we can calculate delta AB from the equation. I got epsilon AB times the original length, right, LAB. Right? This equation was derived from the definition of strain. Right? Strain equals delta over L. Right? So delta equals strain times L, the original length. So now everything has been clear. We just need to follow these steps. We will have 3 steps, right? Step 1, step 2, and step 3, right, to solve this problem. So let's look at step 1 now. Okay, in step 1, we know LAB. Right, we know LAB. That is, where is LAB here? Is 720 millimeter. Right, then we know epsilon AB. That is 1870 microstrain. So that is times 10 to negative 6 strain. Right. Then the delta AB equals epsilon AB times LAB. Right. So that is 1870 microstrain times 720 millimeter. So this will be 1.346 millimeter. Okay, then in step 2, okay, we're looking at this equation, right? So we are calculating delta BC. So delta BC equals delta AC minus delta AB. Right, delta AC has been given, so that is 1.692 millimeter minus 1.346 millimeter. So we will got delta BC is 0.346 millimeter. Okay, now we come to the last step, to calculate, to solve the epsilon BC. Right? The epsilon BC equals delta BC over LBC. Delta BC is here, this is 0.346 over LBC, 450. Okay, so we will get a number that is 0.000769 strain. Or if you like to use microstrain, so this is 769 microstrain, right? Because this equals what? 769 times 769 times 10 to negative 6 strain. That's it.